Hi, everyone. Let's get started. Hi. Hello? Does this work? Hi? Sorry. Okay, this is wrong. Cool. Does this work? Can people hear me? Awesome. Thank you. I am recording. Yes. Okay, cool. So before we start, just a couple of announcements. I think there was a bit of confusion earlier in the week about the office hours. So sorry about that. Abhishek's office hours are in person on Monday. Because in the pre-survey, several folks said that they would like at least one in-person option. So Abhishek, who's in the back, will be in person on Monday afternoons. And I am on Thursday and Khan is on Wednesday. So Khan is tomorrow. Online. Both of those are online. So that's the first one, and the information is all in the Canvas announcement. The second thing is there's a slight issue in the test driver for the homework too, so just please pull from the repo. It shouldn't affect anything that you did because you should just be changing the other parts. The test driver is just like the part that calls init simulation and run one step. So yeah, that's that. And then I made a slight typo in homework 1, which is when you demo the directory, you have to use the --r flag. So in the future, please use the --r flag, otherwise your folder will be empty. And we had a couple issues with that, but we should have fixed them all for now. So yeah, so I also re-uploaded the homework 2 handout to reflect the --r flag. So yeah, please just remember to do that when you upload your code. Thank you. Okay, so today we'll be doing locking and non-determinism, which is a more extended version of the locking stuff that we were talking about in last lecture. So like I said, well, like we were talking about last time, we were talking about determinism a little bit, and specifically a program is deterministic if given an input, if every memory location is updated with the same sequence of values in every execution. That means the program always behaves the same way. And it means that it doesn't necessarily have to be that the updates happen in the same order. The updates can happen in a different order, but each location will always see the same sequence of updates. And so the answer at the end will always be the same. And the advantage of having deterministic programs is that debugging them is much easier because you have one expected output, whereas with non-deterministic programs where the output may change, it's hard to tell whether something is a bug versus whether it's just a variation of the output. But unfortunately, not all of our programs can be deterministic. In many cases, you may need non-determinism. And one way that we implement that is with mutual exclusion. So we were talking about locks last time. So this is just a concrete example of a hash table. This is buckets, and these are your elements. And this is a chain hash table. So when you put another thing in a bucket, it gets added in a linked list fashion. And this is the key. This is the pseudocode to add an element. So you first hash your element, you hash the key, then here we're adding to the head of the thing. So we would set, we would find the slot, which is the head. We would set our element next equal to the head, which becomes the new head. Sorry, we would set the old head to the next thing for this element, and then this new element becomes the new head. Okay, so that is a traditional hash table. And we have an issue if we just directly try to concurrently parallelize over the updates. So suppose that we wanted to add both these elements, 81 and 37, and suppose that they both get hashed to the same bucket. And if we didn't have locks or mutual exclusion or anything, this is like the code, just copied twice. And we have 2 elements, X and Y, right? And we have these 3 operations, but each one of these threads has to do the 3 operations. And so if we have this interleaving, we determine the slot for the first one, and then we set the first one's next equals to the slot head. And then let's say then we executed all of thread 2 of doing the second element. So that would mean Y, which is the second element, goes to the same slot. Then Y next also becomes the head. So yeah, so both of these set their next pointer to this old head because so far it hasn't been updated. Because the next step after that is changing the old head to the new head. And so now we've lost the first update because, we've lost the second one because table like this the head became Y, and then next in step 6, the head became X. So absent locking or mutual exclusion, we would lose the updates if we didn't do something more clever in this case. Okay. The high level reasoning behind this is that we need atomicity in our operations, in that like in the previous operation, we needed to both set the next pointer and update the head in one single go. Otherwise, it would get overwritten in that example. And so we have a sequence of instructions and it needs to be atomic. And atomic means that the rest of the system cannot view them as partially executed. So either you implement atomicity with putting locks around it, or there are underlying atomic like instructions that you can call in your program. Yeah, so atomicity just means that you are guaranteed that all of your instructions in some group are executed all as one. You cannot be partially executed. All of them have to execute. And a critical section is this piece of code that accesses the same data structure that cannot be accessed by 2 or more threads at the same time. So that is mutual exclusion, and we can implement it with blocks. So this is what we saw last time. We have a lock, we have this parallel for, and inside it, if we have some section that we need to protect, like the hash table, we set the lock, we do whatever we needed to do, and then we unset it. Okay. And we talked about mutexes last time. So OpenMP provides an implementation of mutexes. And all a mutex is just some object that allows you to lock and unlock that object. And if you try to lock an already locked mutex, then you will block, which means that you wait. Some thread will wait until that mutex is unlocked, which means that you can now access it again. And so in the code that I just showed, the way that you would lock this is that you would put a lock on every slot, and then you would first lock the slot. You would set both these operations inside the critical section, and then you would unlock it. So you would, in one atomic section, you have to set next and also set the head to the new thing. Otherwise, you lose the insert. And like I said, you can use mutexes to implement atomicity. Okay. So last time I said that determinacy races are when you have 2 parallel instructions accessing the same memory, and at least one of them is doing a write. And if you don't have any determinacy races in your program, it means that your program always behaves the same on a given input, regardless of how the thread scheduling happens underneath. And so this is non-deterministic. So this has a determinacy race because there's no lock on X++. And so you can see whatever at the end. You're not guaranteed that it's 2 at the end. Related to determinacy races are data races, which happens when 2 logically parallel instructions holding no locks in common access the same location, and at least one of the instructions performs a write. So another way to say that is you have 2 or more threads, and they both access the same location at the same time, and at least one of them is doing a write, and they're not using any locks to control access to that memory. And so even if you have data race-free programs, which means that you use locking to protect your data, they can still be non-deterministic, and they are not necessarily guaranteed to be bug-free. So looking at this example that we had again, this is a version of this code that is data race free. So previously we had like lock and unlock at the top and the bottom, but suppose that in an initial version, we just put lock and unlock around each instruction. And you can see that this is wrong because even though it is data race free, like you'll never write to the same location at the same time with 2 threads, the values are not guaranteed to be the same between these operations. And so that's why you need to lock the entire section. However, like in this example, the fact that somebody did use mutexes means that they thought about data races and atomicity. It just means that it is subtle to get it right, because like you have to think about the entire set of operations that needs to happen on the data structure. Okay. You can also have benign races, which are basically you are allowed to, or you can write to the same location in your data structure, but it may not affect the total correctness of your program. So for example, let's say our problem is to just make this array and we set a 1 wherever we have a digit in some input list. And so there's our example input list, like 4, 1, 0, and so on. And our code is just to, for every value up there, we set the bit in this array. This is just like saying what elements we have for a quick lookup. And so if we were to parallelize over that list, we would potentially write to the same location. Like for example, one appears twice in that list. Two appears more than twice, but at least twice. And so two threads might write to this location at the same time, but it doesn't matter because both of them are writing one. So in the end, we would get the same result, despite the fact that we have some write race. And this only works if you can write these array elements atomically. Like each individual write is atomic, but yeah. So yeah, that is how you use mutexes in a couple of examples, and I'll talk about different kinds of mutexes next and how you might implement them. Yeah.
And how do we know that the hardware writes erase atomically? Like, way to know that? Because
Usually you can look it up in the specification for x86. Usually you can, for x86, you can write bytes atomically. So for most common architectures, you are fine. Okay. So there are several or many different kinds of mutexes that you can implement, and these are a few. So the first one is called yielding, which means that when it's not a yielding mutex, when it blocks, or that means like when it's waiting for something else to finish, it returns control to the operating system of that thread, so the thread can continue to do some other work in the meantime. And a spinning mutex consumes processor cycles while it's blocked. So that means it is not doing useful work, but it is not giving up its thread to allow other work to happen. Another one is called reentrant mutex. So a reentrant mutex allows you to hold a lock to acquire it again, even if it's already held. However, but if that particular thread is holding a lock, it can hold it again. But a non-reentrant mutex, which is a more common kind, deadlocks if you try to reacquire a mutex that you already have. Because many mutexes, you can think about implementing them with a bit that's just saying like, is it held or not? And so it doesn't know who is holding it, and it's just waiting for the bit to unset. Then another one, the last one that I want to talk about is more talking about scheduling and how you acquire the mutexes. So like from a programmer's point of view, you're just calling lock and unlock, but you don't know like what order the threads are going to access the mutex, and there's no guarantee. And there's actually very little known about any type of guarantee about when you might be able to hold them, when you might be able to get the mutex if you're a thread waiting for it. So one way to reason about how you might get it is through making some assumptions about the underlying thread scheduler. And so a fair mutex puts the blocks on a FIFO queue, like first in, first out, and then unblocks the thread that has been waiting the longest. And an unfair mutex lets any block thread go next. So it has nothing to do with how long you've been waiting.
So why would we want to have a non-mutex? What's the problem of mutex that is trying to acquire the lock again?
Well, you have, she mentioned, like, you can make a very simple mutex with like one bit that is non-reentrant. But if it's non-bigger reentrant, you have like still more information about who's holding the mutex or what thread is holding the mutex.
Oh,
And
but
also that's behavior that you might not want. So
yeah, but I thought the question is like, why would you ever need a reentrant mutex?
Yeah.
Is that right? Usually you don't. So that's why I think most mutexes are non-reentrant, because it's much easier to implement. I think in some special cases, like if you are not very careful about which locks you grab. So using a non-reentrant mutex, like if you have some locking algorithm that always guarantees that you grab different locks and only once, then you would be fine with non-reentrant. But if you're less careful about how you grab them, or maybe you like have two phases where you grab more locks and you don't, if it's non-reentrant, that you would need to keep track of what you grabbed in the first phase or something like that. That makes sense? Thanks. Okay, so this is some pseudocode about how you would implement a spinning mutex. The spinning mutex is one of the simplest mutexes you can implement. And like I said, in this case, you can just implement it with a single bit. So the way to read this is you start from the top, and then the first line is saying you check if the mutex is free. So that first thing is compare. So you're comparing, mutex is just like a bit. So you're comparing 0 to the mutex, and if it is true, then your mutex is free. We're saying like 0 is unset and 1 is set. And then the next thing is jump to get mutex. So you are going here, and you try to set the, so first you move 1 into this register, which is PAX, and you try to exchange one into mutex. And so, yeah, you try to exchange one into the mutex, and then you check if you were able to succeed. So if 0 is now an EAX, that means that 1 got moved into the mutex, so you were able to hold it. And then if you were not able to succeed, then you just jump back here and keep going until you get it. Does that make sense? Cool. Yeah, and then if you are able to get the mutex, then you just continue onto the critical section. And then once you're done with this critical section, then you put 0, you set mutex equal to 0. And then you release it, and other people can also enter this block of code.
When you unconfuse it,
Sorry?
unconfuse.
Oh, pause is just like, it's like a scheduling operation. So pause means that it's not necessary. It's just some performance optimization in the underlying x86.
What do you mean by unconfused?
I think it just means like the operation pipeline, like, so when you operate, like when you do instructions, there's some instruction pipeline with like different sections. And pause is some performance optimization in that pipeline. I guess another way to think of it is like, it's like a little bit of wait. It's basically like wait. To ensure that you don't just keep trying to get it. Okay, so that is like the most simple mutex that you can implement, which is spinning. Oh, and the most important thing here was that exchange is atomic. So no, if you are able to, you either succeed or fail, but there's no like intermediate state for exchange.
Not sure if it's important, but when do we jump to the critical section?
You don't, you just continue. If you fail, you jump back. And if you succeed, then you keep going.
Oh, I see.
Just to clarify, will we compute like this program is going to run till we get the mutex?
Mhm.
So when do we know that we fail? Like, what is a failure condition?
You mean if you fail to get the mutex?
Yeah. So like, how would that look?
Yeah. So here in this compare, you compare the register with 0. And if this register is not 0, then you know that you failed to get the mutex, and then you jump back to try to get it again. Because, okay, so the way to read this is that you put 1 into EAX, and then you try to put 1 into mutex from EAX. And then you check EAX is 0 or not. Yeah. Does that make sense? Yep. So that is spinning. And then to do yielding mutexes, you just call yield instead of pause. So yield is, so pause is like wait, but you're still using cycles, and yield gives up the thread to the underlying OS, and then the OS can schedule other threads in the meantime. But the rest of it is, let's see.
Okay, how does this thread be awakened?
How does it awaken? So the question is, it goes back into the thread scheduler. So like this operation. So this code is like, it still clearly needs to be executed, but it just doesn't have resources when you call thread yield. So eventually, due to some underlying scheduling, it will eventually get rescheduled. Or we hope that it gets rescheduled.
So thread yield is a function, not a assembly command.
The thread yield is an assembly.
Yeah, but if it's assembly command, then I think it will correspond to some hardware instruction. But I think for here, it's a function written by high level code, and the operating system should provide its functions because it's responsible for CRS.
Yes, I see. Yeah, I guess the operating system would provide the thread yield. Yeah, so that is how you would implement the mutex under the hood. And so, like I said, it's difficult to tell how long you should wait when you have your mutex, because there's two competing goals. One is that you want to claim your mutex as soon as somebody else is finished with it. So you want to make forward progress as fast as possible. But the other time, at the other hand, you want to waste a few cycles. You want to wait a little bit, because if you keep trying to grab the mutex, then spinning and then you're wasting more cycles. So one idea is that using algorithms, one thing that you can do is that you spin for a while, then you yield. And how long should you spin? As long as you take to do a context switch. And so that's within a factor of 2 of the optimal time, because if the mutex is released while spinning, then you can grab it, and that's the optimal time to get it, because that's as short as you could have waited. And if you get the mutex after the yield, then it's it's 2x times optimal, because you spun and then you yielded an equal amount of time. And it turns out that if you do this randomized algorithm, some kind of randomized algorithm, you can do better than a 2x approximation. You can get within 1.58. But I think in practice, usually this one is fine. Oh, sorry. Yeah.
How's that 2x optimal?
This one? So there's 2 cases. So you have two phases. One is that you spin, and then one is that you yield. And there's 2 phases. There's 2 cases. Either you got the lock in the spin phase, or you got the lock in the yield phase, or after you yielded.
Yeah, but wouldn't you consider like after yielding, how much time it takes for you to get scheduled again?
It's assuming like you get scheduled right after you yielded. Like you yield for some amount of time.
Yeah, but that amount of time is variable. Depends on how many other threads are running, and when the overscheduler puts you back again.
Yes, in this, I guess this is like a theoretical thing. This is assuming that you can control your yield.
Okay, so it's assuming that after you yield and the mutex is released, you're scheduled immediately back.
Yes. Yeah. Mhm. I think this is like a theoretical guarantee, but as you said, like in reality, you're not guaranteed to be scheduled. Depending on the scheduler, you're not guaranteed to be FIFO or equal or anything like that.
How long you yield, because the time that you yielded is the time that another thread can do work, so that's still fine, right?
This is a claim about, for one particular thread, like how long should you yield to get the mutex? And like what claims can you make about the worst case approximation about when you get it?
The optimal time, if you're always spinning, that's obviously not the optimal time.
Like if you're always spinning, then you kind of grab it as soon as
Yes.
possible, but that's like, you don't want to always spin because then you're wasting cycles.
You don't need to create optimal because you have to context switch back once you context switch out and then context switch back again.
So you're saying like you spin equal to the context time, and then you context switch, and then you wait, and then you context switch back.
Yes, there are 2 contexts.
Is it two? I guess so, yeah. Do you have to do any context switches if you just spin? No, right? You just grab the lock.
While spinning not, but then you context switch out, you run something and you context switch back.
Mhm.
So we do that.
Yeah, I guess if you count the context, yeah, if you're counting the context switch time, that would be 4x, where context switch is 1. Basically. Because like spin is 1 times context switch, and then to yield you have to do a context switch.
Yeah.
I guess this 2x is thinking that you don't actually do a context switch, you just give up the resources. Yeah. Then it would be 2x, but if you do the context switch in between, then it would be 4, because it takes time to do a context switch. So like you would spin, and then you do the context switch, and then you yield for that time, and then you context switch back.
Oh, yes, okay.
Does that make sense?
Okay.
Do you have a brief description of like what the randomized algorithm is doing? Is it like flipping a coin and deciding what to yield or not?
I'm not totally sure. Let me look it up, but my guess would be that you wait a random amount of time.
Oh, like you spin for a random amount of time before yielding?
Yeah, but I can check the exact details and tell you next time. Mhm. Okay. Cool. So good. So that is how you do implementation of locking, and also how you think about when to wait. So one main issue that happens with locking is called deadlock. And deadlock just means when you have when two threads wait on the same resources, but each of the other threads is holding the resources that you need. So this is an example, you have two threads, thread 1 and thread 2. And so thread 1, you have two resources, A and B. And so thread 1 locks A first, and then it wants to grab B. And then on the other hand, thread 2 grabs B first, and then it wants to lock A. But neither of them can continue because thread 1 is holding A and needs B, and then vice versa for thread 2, it's holding B and then it needs A. So then you stop and the entire program is stuck. So there are several conditions to have deadlock. One, in that previous example, the first one is mutual exclusion, which is that we just use regular locks and each thread has complete control over its resources. Nobody else can enter that section. Second one is non-preemption, which means that the thread holds the resources until it finishes with them. And the last one, which is the most important one, in my opinion, is circular wait, which is you have this cycle of grabbing locks from threads in which each thread is blocked, waiting for resources by other threads in the cycle. So in that previous example, there's just two, one like A and B, and they were each waiting for each other. So there's this classical example. I think it's from I think it's originally from Dijkstra, but it's called The Standing Philosophers, which is a slightly more complicated example to illustrate deadlock. So basically you have these, I guess they're noodles, and then each one has left and right chopsticks, and you need to grab both of them to continue eating. And so you have, I guess in this case, 5, but you have this program and each of them locks. So you have each of them has some index I, and they grab them in the same order, I, and then I plus 1. And then like you unlock them in this sort of order, I, and then I plus 1. And then you do some intermediate stuff. And the issue is that one day they all pick up the one on the left at the same time, and they need the one on the right, but it's not available. And the way that you can prevent deadlock is by providing some order to your mutexes. So assuming that you can linearly order your mutexes, this is just L1, L2 up to Ln is the mutexes that you have. So you need to linearly order them, and then you need to access them in the same order that you gave them. Or you need to grab them in the same order that you gave them. Yeah, so without loss of generality, if you grab L sub 1, and then you try to grab any other lock L sub j, then you're guaranteed that in your order, L1 is less than Lj. Then you can't have deadlock because there's no cycle. And you can prove this by contradiction. So, like I said, you can avoid deadlock if you have total ordering of your locks. And in this example, the way you would do that is rather than doing I and I plus 1, you would grab based on your index, even or odd, then you grab a different order of them. Okay. Another issue that can happen with locking, so deadlock is like a correctness issue in some sense because you can't proceed if you get deadlock. Another issue that can happen with locks is called contention, which is just everybody is trying to grab the same lock. Okay, so let's say we have this example where we want to sum a bunch of elements in an array. So we have some elements, this is like 1 million, and we have an array, and we do some initialization. And this is a very common thing that we might want to do. We want to add everything into result. Okay, so how would we parallelize this? We would add a parallel 4 outside of the for loop, but then we would have a race on result because everybody's trying to add into it at the same time and there's no protection. Okay. So then we have to add some mutexes. So in OpenMP, we would first make the lock and then we would protect the result value with locks. So we would set it and then we would unset it around that. But now everybody has to, this lock serializes everyone, even though we have a parallel 4 here, everybody has to wait and grab this lock. And so this is called contention, and then you get no parallelism. But you can still finish with this, like nobody is circular waiting. It's just that everybody is serialized by this operation. So if you have a lot of contention, usually you either have to come up with something smarter, either a better algorithm or a smarter locking scheme. Okay. And then when you have parallel programming, there's this anomaly or this performance issue that can happen called false sharing, which is not necessarily related to locking, but I wanted to talk about anyway, because it does come up. Okay, so this is the sum example that we just had pretty much. We have this array A and we have a result, and then we want to add everybody into result. Okay, so how might we do this? Like we said, there's an issue if you just put locks around results, because then everybody gets serialized. So one very traditional paradigm that you can do when you try to parallelize like a linear sum or linear any type of operation is that you make these partials. And every thread computes some partial, and at the end you add them all up. So yeah, so previously we just had one value called result. And with the partials, now we have values equal to the number of threads we have. Now what we're going to do is just split up the for loop that we had equal to in chunks, or sorry, this one. We're going to split it up into chunks equal to the number of threads we had, and then each thread is going to compute some partial sum. Like we're just going to divide up the iterations and everybody's going to work on a separate set of iterations and they will not conflict. And then you don't have to use locking at all. So that's one way that you can just totally rewrite your loop to avoid locks. And then, yeah, so then you fill up the partials here, and then at the end, just in serial, you sum up the partials. And that has, in some sense, like perfect parallelism because everybody is separate and independent, and you don't need to do any synchronization or locks. And then you just add them all up at the end, and there are many fewer partials than there were originally. Does that make sense? Okay, but the issue with this is that recall that we have this cache coherence under the hood, which is that if some processor has this value in their cache, then it has to have the same view in everybody's processor. And also that underneath in your cache or in your memory hierarchy, you don't just have single values, but your unit is actually a cache line, not just a single value. So one issue that you can often get in scalability, like I said, is called false sharing, which is that you have independent data elements that are being updated that happen to be on the same cache line, but they're technically separate elements, but they are in the same cache line. So multiple processors might need the same cache line despite updating separate values. So the cache line will have to move back and forth between the threads because each thread will keep invalidating that cache line. It will need to keep switching back and forth. And so like in the thing that we just did, which is that we made scalars into this partials array to do parallelism, the array elements are contiguous in memory. And so two adjacent threads might be updating the same cache line despite updating the different partials. So the solution to this is that you pad the arrays so that you use different cache lines. Okay, so this is just how you would pad that thing. Here in partials, previously this is equal to length num threads. Now it's this duty thing equal to with num threads rows, and each row has pad. We're assuming that you have 64 byte elements. And yeah, and you just fill the partials as before. We're just going to use the first thing in each cache line as our value, and then in the end, we're just going to sum them up as before. Okay. Does that make sense? All right, so in the rest of this, I want to talk about more complicated locking and more complicated synchronization on data structures. So the most traditional or like the most straightforward synchronization that you can do is just locking the entire data structure and operating on it as one thing. And that is really easy to reason about and prove the correctness about, but it doesn't really work if you have a lot of threads operating at the same time, because then you get contention on the one single lock. So instead, what we're going to do is split up the concurrent data structure into different independently synchronized components. And usually what this looks like in tree-like data structures is that you have the node pretty much like in a linked list or a tree, and then you put a lock on each one of them. So rather than locking the entire data structure. And so threads will now conflict if they want to access the same node or the same component at the same time, but they will have less conflicts than if you if you put a lock over the entire data structure. So this is like a node. In your traditional linked list, you have data and then you have next, and now we just add lock to it. So like I said, we're using this linked list example and this very simple linked list. We have a sentinel in the beginning, we have a sentinel at the end, and then we have some elements in the middle, here A, C, and D. And the way that you usually operate on this is that when you want to add some node, for example, B, let's say we're keeping this thing in sorted order, we are inserting B between A and C, and we change A.next pointer to C, and then we put, or sorry, we set A.next equal to B, and then B.next becomes C. And then, yeah, so that's how you add things, and when you remove things, then you just set next equal like the next. So like I said, for coarse grain locking, a very simple thing is that you just lock the head. And that is easy and clearly correct, but if you have many threads, then it doesn't really scale that well. So instead, we split the entire list into nodes, and every node has its own lock, and we can work on disjoint parts or disjoint pieces of the list without needing to do synchronization between them. And the most easiest way to do this fine grain locking, or in my sense, the most traditional way to do it is called hand over hand locking, which is when you use two locks to traverse through the list. And we need two because one does not guarantee that the things that we need to change are going to still be stable. So for example, suppose that we only had one lock, like here, this thread 1, and we wanted to delete the node C. So we can lock B, and then we need to set B next from C. But however, an issue with only holding the one lock is that B might get deleted at the same time. So if you can currently delete node B by setting next from B to C, then A will go to C, and B will get deleted, and C will still be in the data structure. So the main insight behind hand over hand locking is that if you lock a node, nobody can delete, or yeah, if you lock a node, nobody can delete your successor. And if your thread locks the node to be deleted and also the predecessor of the node to be deleted, then they'll work. So that's why you have to use two locks. So to delete C, we have to lock both A and C, and we would take A next. So here's an example, a more concrete example of how it works. Suppose that you have two threads here, T1, T2, and you want to remove nodes B and C. So first, somebody has to acquire the lock on the sentinel, and the other one has to wait. So suppose that T2 got this lock on the sentinel. And now T2 can grab the next one after the sentinel. So it has these two. And then it can move on. So it releases this one and then grabs this next one. Yeah, so before you lock B, you have to release the sentinel and then try to grab B. And then T1 can now grab the sentinel because it's released. And then, yeah, so to move on, to delete C, you also need to move forward in T2. So now T2 holds B and C, and T1 can move forward to sentinel and A. And now T2 can remove the node C by setting B next to the end. And then T2 is done. So now C is deleted and B just points to the end. And now T1 wanted to remove the node B, so it needs to move forward. So now T1 releases this one and grabs this one, and then it can just swing the pointer to the end. So to remove the node, you have to lock the node itself and the predecessor. Does that make sense?
Each node has a lock,
Each node has a lock.
and you need to grab the node you want to delete and its predecessor.
Yes. Yeah, and you need to release before you grab the next, like each step of this iteration, you try to grab next, and then before you grab next, you have to release previous.
The one a thread can only have maximum of 2 locks.
Yes, exactly.
But so in this example, like you'd also need to lock whatever you're setting it to, right? Just in case like somebody else deletes that.
You would also have to remove what you're setting it to. So you cannot, nobody can delete the thing in front of the thing that you're trying to set it to, according to the scheme, because you need to hold your success or yourself and your predecessor. So if they're trying to delete like, so for example here, if somebody else is trying to delete C, they would need to hold C and Sentinel.
Yeah, but
Or sorry, they need to hold C and T.
and B, yeah, but then you'd have to like set B, like B's next to that blue node, but somebody could delete like that blue node. Right?
Blue will never be deleted. because
Oh,
blue is-
yes. But then you already have C now.
Yeah, so if you delete blue, you have to hold C and blue.
Okay.
So then, that's why you need to.
So I mean, like what if like I wanted to set, oh, I see what you did. Okay.
Yeah, it's a little complicated. For sure. Yeah, good. So that is hand over hand, and that's kind of like the most straightforward fine-grained synchronization method, is that you just grab, you release previous and then you grab next. So that's why it's called hand over hand.
But I'm a little confused about the hand over hand. Why to delete the node, I just have to lock its own and its predecessor, but why I have to lock the initial node, the root node,
Why you have to lock the root node?
the blue one, the first blue one. Yeah.
Because you have to start somewhere to do your forward traversal.
Oh, got it.
Yeah, because and this is a linked list. So, yeah. Question. Okay. Yeah. So hand over hand locking is this fine-grained synchronization method, and sometimes it's better than coarse-grained locking because those can traverse in parallel. But depending on your level of contention, sometimes it can be worse because you may not have enough. Like the reason for this is to avoid the contention, but if you don't have enough threads, then you just added locking overhead without any reason for it. And it's not ideal because many locks may be acquired and released. And like you said, everybody has to grab the head first. So you still have to synchronize on that. So we can do better with something called optimistic synchronization. And the high level idea behind optimistic synchronization is that you don't, most of the time, like when you do the list traversal, you're grabbing these locks, but you don't need to edit everything on the locks that you're grabbing. Yeah, you don't need to edit everything on the locks that you're grabbing. And so what you're gonna do instead is traverse the list without locking. And then this is not guaranteed to be that you're able to write to this if you just traverse to the list to the position that you need and then stop and try to edit. So you still have to grab locks, but you're just not grabbing all the ones along the way. So instead of doing hand over hand, which is like hand over hand means like if you grab the locks that you were supposed to at the end, you can make your changes and you're guaranteed to. But here, if you grab those locks at the end, you still have to do some checking and you may have to like roll back to the beginning. So it's kind of like a very different way to do it, but it relies on the idea that oftentimes people are not changing stuff around you. And so that's why it's called optimistic, because you kind of hope that nobody is changing stuff around you, but if they do, then you have to start over. So in this example, we want to add this node C. And optimistic synchronization, then you just traverse forward through the list and you stop when you get here. We're trying to add a C, so we have to grab B and D because C is going to go in between them. And then we check. So you grab just the two locks, not like hand over hand where you grab them all along the way. You just stop and you grab the two locks, and then you have to do some checking to make sure that things are okay. And things may not necessarily be okay. So one issue that can possibly happen is that somebody is trying to remove the predecessor of the thing that you are trying to add. So you are trying to add C here, but somebody else is removing D. And so if you just, yeah, so T2 is here, and then T2 has grabbed these two locks. And yeah, so this A next pointer swings over to D. And so trying to add something between B and D, like you as the third one still have hold of B and D. But now B is no longer connected in the data structure, so if you just at some point after this grab the locks in B and D and try to add C, then it's not gonna work because B is no longer connected. So that's one issue that can happen. And the way that we solve that is, yeah, like I just said, now B is disconnected, so you can't just grab the locks and directly, like when you grab the locks, you can't just directly add your thing straightforwardly. So what we're gonna do is we have to check that B is still reachable to be able to add it. And so we grab the locks on B and D, and then we have to traverse from the beginning without locking to check that B is still reachable. And if it is, then we know it's safe to add. Because since we held B and D, we know that B cannot be deleted. So like if we get here, then it's safe to add C. And if it's not, then you just have to release the locks and start over.
Track if B is reachable using whether its lock is still, the lock is still there, because if we delete the node, we may release its memory, right?
If we release the node, then it may be even worse because then you're trying to access memory that has been freed.
Oh,
Like from a thread point of view, like think about the code that you're writing. Your code is just like calling next, and then your code is just calling like, I guess you have B next equals C and C next equals D and so on. But if B is garbage, then you may get even worse results. Or maybe it won't crash, but B is disconnected and B is garbage if you have freed it.
so before every calling of next, we should check if it's node is.
Only when you have grabbed the locks on the nodes that you want to add this thing between.
For example, before thread 2, so before thread 2, call next on B is deleted by thread 1. Then when thread 2 call next, it will call something.
Yes, so like, okay, so when you want to insert something, you have basically like you have two nodes A and B that you're trying to add your element between. And you just have those in your code, and your code to insert is just A next equals the thing that you're trying to insert. The thing that you're trying to insert next is B, for example. And but I'm saying that if you're just holding on to those, like in your program, but as threads move and do stuff in the, like while your thread is executing, it's not guaranteed if you're not locking that thing that thing is still valid at any point. You may, okay, so let me try to say this in a different way. So if you check, let's say that thread 2, thread 1 does this optimistic pass, and it sees B and D, and it's like, okay, I need to insert C between B and D. And it tries to grab the locks on B and D. But in the meantime, thread 2 grabs the locks on A and B, and it deletes B. It can do that because thread 1 has not locked B. Thread 1 is just trying to get B. And then, so thread 2 deletes B, and thread 1 is still trying to get B, but it has not yet.
When P1 is waiting on B and then P2 deletes B, wouldn't the cache line get invalidated for T1 and then you have to check again if it'll have to fetch B again from the memory? It will find that B is not there. Oh,
You're not guaranteed to, how would you know that B is not there? Like if T2 had freed B, like you can read freed memory. It's wrong, but you can do it. Or your program may, depending on what you're running under, like you may crash, or you may just silently you may silently read garbage, or you may silently read something correct, like B's pointer may still point to D.
Yes, yeah, that's my point actually. So I think before every call of next, we should check if this node is validated.
Before every call to next.
Otherwise, for example, B is deleted by T1, and considering that we don't try to insert a node between B and D, we just, another thread just is on B, and B is deleted. And it calls next, and
Another thread is on B and B is deleted.
it calls next, and then that thread crashed.
You cannot go to B because B is locked. Like another thread cannot be on B while B is held.
But you said traversing doesn't require lock.
It doesn't require you to hold locks, but you cannot traverse while there are locks in them. Like, sorry. Traversing does not require you to hold locks, but you cannot proceed if somebody is holding a lock.
How do you know if this lock is held by another thread without quarrying? Oh,
You can check it.
oh, you can, yeah.
You can check the bit. Actually, no, hold on. Let me think about it for a second. If you, okay, so if you have two threads and one is holding B and then one is trying to delete B, if you have an issue that B becomes invalidated,
The second thread is not holding B, it's just on B.
it's just on B. And then somebody in the meantime deletes B. Yeah, so I guess the easiest way to do it is just check the bit.
But
But can it
if we
even
want to track,
happen?
we have to start over.
Huh?
But if we want to track if this node is validated, we have to start over from the beginning. And every core next, we have to start over, which is,
Are you not just talking about validating like, oh, you're not talking about just validating this next point, are you going to validate from the beginning?
yes.
Can you just validate next? I guess the issue is like, what if? Maybe. Actually, maybe it's okay, because you're never guaranteed, so this next pointer may still be valid, because you're guaranteed to never delete D at the same time as D. Because like you have, because of the way that you're doing the two locks, like if you want to delete D, you have to hold both B and D.
Yes, the next pointer should be fine, but
So I wonder
Yeah,
if
you
even
are-
if you delete D, can your next pointer still be valid? Like, you don't, you just keep next, like you keep this next pointer, you keep holding on to these two elements.
But what about thread 1 or 2?
I think we're talking about the case, not that you're trying to insert, just that you're trying to do traversal. And we're talking about the case like, can you invalidate this next pointer while B is getting deleted? Or sorry, can you be trying to do this traversal while you're deleting B? In such a way that this next pointer is invalid? Actually, I think, no, I think even if you delete B, like if you said, it's too complicated to keep checking the lock, so the only case that this is bad is if B also goes away. But I think that can never happen, because you can only ever delete. Like, if you're holding these locks, you can only ever delete B at this time.
yeah, but another thread three did B. And you are holding two,
Another
three.
thread can delete B. Oh, if you're holding both B and D, and then you get rid in the meantime, that delete both of them? Then you have to start over. And then have one. No, it shouldn't be looking. Yes.
So can you share the question?
Oh, yeah, the question is, if you, can you concurrently delete the node that you're trying to traverse from? Does that make sense?
So things, P1 is still traversing B, at the same time, P2 deletes B.
Yeah, so P1, let's just say is trying to, I don't know, let's just try and say it's like, this list keeps going, and it's trying to do some stuff later.
Okay.
And it's traversing forward just optimistically, and T2 removes B in the meantime. While T1 happens to be on B. Is that possible?
So I'm guessing, say, P1 has some code onto these resources, but not the log. It's the cache, and then if P2 frees the memory for B, the cache line will get invalidated. P1 have to fetch B memory again. If it's trying to access anything.
But like if B is released, then what is it fetching?
Released by T2.
Yeah, like T2 is removing B. T2 is deleting B,
Yeah,
and T1 is having to hold B at the time, like. T1 is doing the forward traversal, and then it has current is B and next is B, for example. I guess just to do the forward traversal, you only need current, and you're just calling like current equals current.next or something like that to do this forward step.
So aren't we forced to do hand over hand, trying to do the traversal after we acquire the lock? Because otherwise, if like something is like we're sitting on a deleted node, and it's like one thread is doing the traversal without hand over hand. And it's sitting in a node that's about to be deleted by another thread, then if that is deleted and we try now to call next the first thread, we'll probably have some site fault because that's not memory that we have allocated to ourselves. So aren't we then forced to do hand over hand if that issue comes up? I can't think of the answer.
You're saying like, if you run into issues, then you have to do hand over hand from the beginning?
Yeah, like let's say like for the step where we have to like delete a node for one thread, right? You first acquire it, first go to the node itself, you acquire the lock, and then repeat the traversal again, right? To make sure that you're at the valid, you're at a valid part of the list. But when you're repeating that traversal, like say you encounter another thread is deleting another part before. Then like I guess it's like a similar case again, but at that point, like if it's trying to delete it, like you would be forced basically in the retraversal to do a hand or overhand, because otherwise there's a possibility you could be accessing memory that's thrown away from you and find that thread. If it's deleted at some instance while you're traversing.
I see, so you're saying like, if you try to grab these two and then you can't, then you start over and you have to do hand over from the beginning. I think you shouldn't though, like in traditional optimistic, you only have to grab the two at the end, and you just keep restarting if you fail.
Maybe by deleting you don't free the memory, like you just,
Maybe you just keep
Have
it,
a
and then
reference
you're
counter.
guaranteed that the next is valid.
maybe have a reference counter or something that says someone's on B, and then you do
you
the
have to know some.
traversal from the
B
beginning.
is still valid.
You have to know somehow that B is valid.
Yeah.
Otherwise, it might set fault.
Yes.
Oh, we can have a reference.
That's all, like, you don't free it instantly, you just free it when the reference count falls to 0.
Yeah, you can.
I
Yeah,
think
that's possible.
we-
I'm trying to think like, is that necessary? Like, it would work. But I don't remember it being necessary. But maybe for now, we can just say that's how you would do it, and then I can think about if there's a more straightforward one. Okay, yeah, so going back to this, the main idea is that you check if you can grab those two locks, and you also, once you hold the locks, you have to start from the beginning and check if it's still connected. Another issue that can come up is that if you're trying to add something, so here we have T1 trying to add C between B and D, but in the meantime, thread 2 can also try to add something between B and D, like B prime. And so if you held, oh, this one should be C actually, but so suppose that thread 2 has added B prime between B and D, and now thread 1 holds the locks on B and D. And then it sets B next equal to B prime. And then you would lose this answer, or sorry, it sets B next to C, and then you would lose this B prime.
When T2 is updating next point of a B, wouldn't T1 have to fetch the memory part again and have the ability to?
That's how you're gonna fix it, is you just have to check that D is still B next. Like normally you wouldn't check it. Like normally, if you're just inserting two serial links, you just set next equal to whatever it was. But in this parallel version, now you have to do validation that that pointer is still valid. Or that, not that it's still valid, but that it points to what you think it points to.
No, I'm saying when that next pointer is updated to some B dash. P1's cache will get invalidated. It'll anyway have to fetch the next pointer again from the memory. It
You don't
might-
necessarily have to, like, if you held be next as like a, just like a side variable.
Yeah, but then the P2 will update next pointer.
If you like held it not as a pointer, if you just held it as like a value. Yeah, if you were just checking be next straightforwardly, then you're already implicitly doing the validation, which is that. But you have to check that. I mean, you're calling be next. Yeah, you're calling. I guess like so. In the meantime, P2 would set B next equal to B prime, and then P1 would also want to set B next to this is C. And so you have to make sure that B next is still D, because you want to add C between B and D. Make sense? Okay, yeah, so the way that you saw that, like you said, is you make sure that D is still next for B. Okay. So why is it fine to do that? If B and C are locked, then you can still get to B, and neither B and C will be deleted. And yeah, so why is it good to use optimistic synchronization? You would have limited hotspots, so you would have less contention, specifically, you would have less contention on the head, and you would have fewer lock acquisitions and releases because you would only try to grab the 2 locks that you need, and you may have to do some validation and you might have to start over, but if the contention is not extremely high, then you probably won't. And it is good to use optimistic synchronization when the cost of scanning twice without the locks is less than the cost of scanning once with the locks, because otherwise you would just use hand over hand. Okay, so I think, yeah, I do have a little bit of time. So I want to talk about doing concurrency control in a more complicated setting. Should I stop?
No.
Sorry.
I've never seen.
Okay, so we were talking about mutual exclusion before. There are more complicated locks that you can implement. So one traditional one is called reader-writer locks, which is when you allow concurrent access for read-only operations, but you make exclusive access for write operations. And so multiple threads can read the data in parallel, but you need to grab an exclusive lock to write and modify the data, and nobody can read while the write lock is taken. And the way that you would implement that, you can think about it, implementing it as an array where you have where you have one flag if it's in write mode, and you have a bunch of counters for in read mode, and then the number of counters can be equal to the number of threads. That's the easiest one, and then you just set a bit if your thread is taking it in read mode. And everybody else has to stop if it's in write mode. Okay, so remember that we talked about B trees some time ago? We also talked about B plus trees. And the goal in this is that we want to read and update the B plus tree at the same time with multiple threads. And so there are 2 kinds of issues. One is if you have threads trying to modify the contents of a node at the same time. And the other one is that you might get changes in your tree structure while you're traversing the tree through merges and splits. So in databases, they call this latch crabbing, and they use the term latch where we would use lock for shared memory implementation. So I'm just gonna call it latch crabbing, but it's the same idea. Like they call lock something separate about like transactions, but for us, latches and locks are the same thing, which means that they're on a per operation basis. And the protocol to modify the B tree is using the reader-writer locks, get the latch for the parent, get the latch for the child, and then if it's safe, for some definition of safe, release the parent and keep going down the tree. So this is sort of like hand over hand, but just in a tree rather than in a list. And safe means that the node is not going to split or merge when you update it. And the case condition for safe is that if you're inserting, it's not full. And if you're deleting, then it's more than half full. So you have enough space either to insert or delete. Okay, so for finds, it's very straightforward. You start at the root and you just keep grabbing the reader locks on the way down. And then you unlock the parent, and there's no issues of safety because you're not writing. So that is pretty much exactly like hand over hand, but just top down. for insert and delete, we're gonna start at the root and go down, and we're gonna take right locks as necessary. And once you grab, again, it's kind of like hand over hand, but it's not, but you may hold more than 2 locks at once. And once you grab the child, then you check that it's safe. And if the child is safe, then you can release all the ancestors because you know that you're not going to have to pop up your inserts. So as an example, let's say you want to find 38. So you start by taking the read lock at the root. And then you go down 1 level, following the pivots, and you get here, and now you know that it's safe to release the lock on the root because you're done with that. So you release it, and now you keep going down. Now you go to this node. And then you take the read lock down here, and then you can read 38. Yeah, so then you found it, and you just needed to take the read locks top down. Another example, slightly more complicated, is let's say we want to delete 38. So we take the right lock on the root. And we go down 1 level, and we don't know yet how this deletion of 38 is going to affect lower levels. So if this deletion of 38 will change B, yeah, this deletion of 38 might change B, we don't know. And so we have to keep holding the right lock on both B and A. Okay, so now we keep going, we're still holding A and B. And now we look at D, and we know that we have to delete 38 here, but there's enough space because there's still going to be 44, so it's still going to be at least half full. And now we know it's safe, so we can release A and B. Okay, so we have to delete 38. First, delete 38. So we have to hold on to D, and then we're going to keep traversing down the tree, because if 38 is here, then 38 must also be lower in the tree, because this is a B plus tree. So we are going to hold on to D, and we are going to now grab H, which is 1 level down, and indeed we find 38. And because we have the right locks on both of these, we can just delete it. And we do have to now promote 41 up here. We keep this node down here. This used to have 38 and 41. Now 41 becomes the new pivot.
So if we have a lock on a node, then we cannot further traverse the subtree by any other type, right? We gotta just wait until the parents.
If it's in right mode. Yep. Okay, so now that is done, we have deleted 38.
So I can imagine a scenario where we kind of delete a node, and as you've shown right now, we've gotten into some right subtree, and then we'll lock basically a parent and then node again. But it might happen then basically after deletion, we might rebalance the tree and then kind of like take this node and delete node, take the child and kind of take this 38 and then pack it into other leaf node, right? So it
Like
might
we have to
be-
do a merge. Like we have to do a merge.
Yeah, exactly. But there is also might be another case where we deleted something from the left subtree where we didn't have any lock from the strat that we considered before, and the leaf, and then there is the similar situation basically where the child gets deleted, but the very first thread doesn't know about that, and it will try, because of the references, kind of to rebalance into the non-existent child, and the question is whether it's possible. Probably not, but I wonder why.
Can you repeat it? I don't
think it's a bit too complicated.
So,
I'll try to-
let me try to understand. So the issue is, like, you may get simultaneous merges
Yeah.
of nodes, and but you cannot get simultaneous merges of the node that you hold the right lock on,
Mhm.
because you're holding the right lock. So you're saying, like, if, for example, if you did have to merge like here and here, how would you do that? Well, in this case, you're holding D, so this
Yeah,
is
yeah,
still a
but
child.
suppose this
Suppose
child
this is
was-
not-
was
it's
in
like
the
elsewhere?
subtree, yeah.
You would have to grab the rightmost. You'd have to grab this one in
Okay,
right
yeah,
mode also.
makes-
But there's no deadlock because you still respect total ordering, top, down, left, right.
Yeah.
Does that make sense? Okay. I am actually out of time, so I will finish this next time. Thank you.